Hi, my name is Manish Gupta, and in this video, I'm going to talk about deep networks with large output spaces. This was the first effort on trying to use deep learning models for extreme classification problem. So recall in the extreme classification problem, you have a data set such that it's a multi-class classification problem or a multi-label classification problem where the data set has a very large number of labels, up to millions or billions of labels, right? And what you want to do is to do multi-level classification in such a framework. Now, of course, one could think about using typical deep learning kind of models so as to do these tasks. Now, these kinds of tasks, of course, too many labels is not very common. But ImageNet 21K task itself had 21,000 labels. If you think about next word prediction itself, it also is about classification in a vocabulary space of several tens of thousands of labels. Specifically multilingual next word prediction kind of models have to deal with hundreds of thousands of labels in the label space. Now, these are all examples where extreme classification kind of solutions are applicable. However, the key bottleneck for extreme classification using neural networks or any deep learning mechanisms is in terms of computing the softmax at the last layer. That softmax computation is super heavy. And the softmax computation basically involves this matrix multiplication of the weight matrix with whatever the activations in the previous, in the layer just before the output in the previous layer, right? And then applying the softmax normalization to it. So this computation, this huge matrix multiplication, and then final softmax computation is what is extremely time consuming, right? This is how softmax is basically applied. Now, so the same kind of thing also holds for logistic regression kind of classifiers, where essentially this logistic regression layer or the softmax layer are the most time-consuming thing in extreme classification scenarios. That's just because the number of classifiers W are pretty huge. Of course, X is just one representation, which is coming from the previous layer, but the number of classifiers W are too many. Okay. Of course, you have like one classifier per class. So you can think about this as the W weight matrix that you have to multiply. And then if you look at the weight matrix is basically, let's say, if you have some previous layer and then there is an output layer and then there is this weight matrix W. So let's this previous layer size be some S, and then the overall final size here is L. So essentially, if you actually look at the weight matrix W, you can think about it as having one vector of size S per label. So you can call each of those vectors as classifiers. Now, if I think about any particular data point, even in an extreme classification scenario, not all classes are relevant to any input example. Okay. Therefore, when I'm actually computing this dot product between the output from the layer S and trying to multiply it with W, so when I'm computing this dot product W transpose X, I really do not really need to compute the dot product for all of those classes. Maybe I can just compute for K classes which have highest probabilities, because typically in all extreme classification scenarios, we are only interested in the top few classes. Given an image, I only care about the top 5 possible class labels. Given a query, I only care about top 5, top 10 matching documents. Given a particular query, I only care about top 5 ads that are relevant to it, and so on, right? So therefore, can I basically just pick up somehow only top 5 classes and then compute the dot product with them is the basic problem to solve. Now, how do I basically get these top most similar K vectors? And if you are essentially from hashing kind of literature, if you basically have worked with hashes, specifically something called as locality-sensitive hashes, you would remember that K nearest neighbors can be actually computed really quickly using hashing. Okay. So somehow the problem to solve is how to get K vectors from W with largest W transpose X, right? And you could use various kinds of hashing techniques as to do that. In this particular paper, the authors have used winner-take-all hashing. Now, winner-take-all hashing basically involves two simple steps. You essentially take all of these vectors from W. So all of these vectors from W, each of them, you do p distinct permutations of these vectors. So you permute them, right? So essentially you do p different permutations. and you record the index of the max value of the first k element. So after you do p different permutations, you take the first k elements from these p permuted vectors, and you take the max value, and that's basically the hash value that you obtain uh, for a particular vector, for a particular row in this matrix W. Okay. Using this particular, using this particular hash value, you're going to look for collisions for a particular new data point X. When a data point X comes in, you're going to find top key collisions in the hash table lookup, and then that gives you your k rows from this W matrix, or your k vectors from the weight matrix, k labels in that senses, which are closest to the data point X. And then you're going to do matrix multiplication, add bias, do softmax, and that gives you your WTA softmax. So compared to the traditional softmax, WTA softmax differs in this hashing, usage of hashing, and therefore computing the k closest weight vectors. Okay. So in a traditional softmax, when you get the output from the previous layer, you do matrix multiplication with W, add the bias, and therefore get WX plus B, and then you apply the softmax on top of it, softmax activation on top of it, right? But that's the traditional softmax. In WTA softmax, what do you do? When you get X, you actually don't multiply with the entire W. That's too time consuming. So therefore, you do a hash lookup, look for the collisions, and then you get the k vectors only. And then you take those k vectors from W, do a matrix multiplication with X. You don't do the full W transpose X, but just those k vectors with X. And then you add the bias, do softmax activation, and that's your WTA softmax. Now that's at inference time. Now, what do you do at train time? Do you do this at train time as well? Of course, you have to do it train time as well. Otherwise, training will be super slow, right? So at train time, I mean, essentially, this picture shows you what happens at train time. So you have your Ws, you have randomly initialized your Ws to begin with. You take those Ws, you hash them in the hash table, right? When you get the output, the activations from the previous layer, you also hash them. And then you look up into this hash table, get the bucket, look at the collisions, and that gives you your KWs, which are relevant. You multiply only those k vectors with X, and then you add bias, apply softmax, and compute the final prediction. Now, at train time, you must compare this prediction with the ground truth labels and then do backpropagation. So you do backpropagation by updating only the parameter vectors of those retrieved k classes, Okay, so that's that. Now, of course, you do not. You do want training to happen for all positive classes. So therefore, besides the k-retrieve classes, to this set you also add all the positive labels at train time for an input example. Okay, so remember this you do, of course, only at train time because backpropagation happens at train time. The gradients are going to be computed only for those classes which were active, in the sense that either they were retrieved in the top k by the hashing logic, or they were actually positive labels as defined in the ground truth. So this thing is basically like doing sparse gradient updates. Now, these sparse gradient updates have two benefits. First, they're computationally efficient, so training is faster. And second, they also help you look out for hard negative mining, right? So essentially, what you're doing is you're sort of training using actual positives because you added them to the set for which you're going to compute these gradients. And then you also took those negatives, if at all they were there, negatives, right? Which were very similar to the actual data point, to the actual positives. Okay. So therefore, you essentially are also doing hard negative mining while doing this hashing kind of WTA softmax. Now, the problem is that at train time, these weights get updated over time, and therefore the hash tables need to be updated as well. The bucket to which the particular hash belongs to needs to be updated. Now, if you keep doing this very frequently, then training is going to be super slow. And therefore, what the authors have proposed here is to do this refresh of the hash tables periodically. So you don't refresh them in one go for all the classes. Well, you update for a few classes in this batch, and then the next batch you'll update the next few set of classes, and then the next batch another set of classes, and so on. So slowly you update one by one all of the classes in the entire hash table, and you do it periodically. So maybe you do it after every 1,000 steps or something, right? So that's that. Now, how does WTA-Softmax compare with the traditional softmax and the hierarchical softmax? So if I talk about the step time, so every step of WTA-Softmax, they observed on their data sets that it is about 4x faster compared to traditional softmax, but 4x slower compared to hierarchical softmax. Hierarchical softmax is still more is still faster compared to the WTA softmax thing. Now, they did experiments over multiple data sets. I'll talk about two of them. So they did experiments on LXNet, on ImageNet. So ImageNet 21K, where the idea is you have an image and you want to classify it into a few categories out of 21,000 possible labels. Okay. They use the standard LXNet architecture. And here are the results of these experiments. They tried with batch size 1, 8, up to 64. They also tried with how many collision buckets do you have. So you have like sorry, how many k do you take? How many retrievals do you do, right? Not collision bucket, sorry. From the same collision bucket, how many retrievals do you do? So k retrievals, so you could do like 30 different labels or 3,000 different labels. Of course, if you have 3,000 different labels, it will take much longer because you have to do W transpose X on all of that and compute softmax on top, right? But then, so therefore the speed up is lower if you have larger k, but the speed up is much higher if you have smaller k. Similarly, the speed up is super high if you essentially have batch size equal to 1. Okay, so that's that. However, all of this has implications on the accuracy as well, right? So in the k that are chosen, you may not the hash tables might have ignored some of those actual labels. Okay, so what is observed is that about 20x speed up basically leads to about 85% accuracy. So if your batch size is 64. If your batch size is 64, about 20x speed up you can actually obtain compared to standard softmax with only a loss of about 15% in accuracy. Now, clearly, if you there's a trade-off. So if you want 95% of the actual accuracy, you essentially get a 5x speed up. Okay. And there's also comparison on the video identification task. So video identification is the task of predicting the ID of a video based on its frames. So basically give frames as input and some embedding computed on those frames. And you want to predict the ID of the video. Now, for this particular task, they essentially use the sports 1 million data set. So you have lots of videos, lots of labels. And the comparisons are done with respect to both the traditional regular softmax and the hierarchical softmax. So in this first chart, you see comparison with respect to the compute. So with respect to the number of steps, and this is the accuracy on the y-axis. And what you observe is that if you allocate similar kinds of compute for the training purpose, you observe that WTA softmax gives you much better accuracy compared to the accuracy that you can obtain using hierarchical softmax or regular softmax. Now, also they compare with respect to the time of training. So essentially, even from that perspective, you observe that WTA softmax can lead to very accurate classifiers compared to the regular softmax or hierarchical softmax, given the same amount of compute time. Okay. So in summary, softmax layer in deep learning models is the main bottleneck. And this bottleneck is super huge for extreme classification kind of tasks where the number of classes are extremely large, right? And therefore, in this paper, the authors actually proposed to replace the matrix multiplication in this last layer by hashing, and then compute dot products for a very small number of class labels. WTA softmax was found to be much faster compared to the traditional softmax without much loss in accuracy. In some ways, in some cases, it actually leads to improved accuracies as well. Okay. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.